Simple Design Deeper Look Tech Talk. Today, our speaker is Iurii, our senior software engineer, and he will share his knowledge. At first, he will share his knowledge, and then you will have possibility to ask some questions. I guess we can start.
Okay, then. Hello, everyone, and thank you for joining today on this Tech Talk. So, for starters, a few words about me and why should you care to listen to me. Within my 10-year long career, I've been working with a number of tools and technologies. I've been a team lead and team manager, returned to the development roles and worked with a number of product companies as well as outsourced ones. And I did so many mistakes in my career that I learned a lot and here to share about them. So in this tech talk, I will refer a lot about clean architecture and clean agile, both authored by Robert C. Martin, also known as Uncle Bob. You may know him as author of popular Clean Code book as well, member of the Snowbird meeting, where originally Agile Manifesto was written, and one who originally assembled the S.O.L.I.D principles in his paper in year 2000. So I'm really taking information from the original source. Let's start with a little agenda. Can you raise your hands if you saw my previous talk? You can do the hand stuff here in the chat. Yes, I see some people saw. Okay. For those who did not, do not worry. It's not mandatory to see the last one to understand the current one. So I'd recommend to check it out in the recordings to have a more complete context. So today we will have a small recap of the last talk. Then we will talk about simple design on the middle level of the code, where classes and functions are the topic. Where we will cover the S.O.L.I.D practices in detail, S.O.L.I.D principles in details. Then we will see how the same principles and approaches apply on the component level of the software, and we will finish with a few tips on delivering your changes without the pain. So about a month ago, I made another talk about the circle of life. And today we're going to dive deeper into one of the sections in here. More specifically, the technical practices and simple design in particular. In Agile and extreme programming, we use these practices to define what to do to deliver successful projects. The list of practices here is grouped in 4, and the outer circle represents the business practices, middle circle team practices, and the inner one are technical practices. We've talked last time that unit tests and refactoring is part of the task and not a separate thing. And we've talked that simple design is a goal of refactoring, while unit tests and test-driven development specifically is one of the tools to achieve it. Simple design here is a practice that guides the team to prevent the wasted effort. It is also a practice of writing only the code that is required with a structure that keeps it simple, smallest, and the most expressive. But why it is so important than the rest of the technical practices, or there simply to support and enable this one? Why it's so important to keep stuff simple and expressive? The answer to answer this, we have to understand the target audience of our code. Who do we write code for? You can write in chat, or you can just scream, right? And unmute yourself and scream. Any ideas? Okay.
Well, for client, but I think I heard not stream, but scream.
Yeah. Yes, you can scream. Yes, I I do see some very good responses in chat as well. Thank you, Vladislav, and thank you everyone who answered. So our code runs on CPUs on a different architectures, but it's not the one we like. It's not the code that we write. It's in bytecode. We would write the code for CPUs. If you do this, like, you should then go and fetch book on assembly language. CPUs do not care about the elegancy of the data structures and expressiveness and variable names, as long as you do not create an infinite loops. Interpreters and compilers that consume your code to produce the versions that CPUs and virtual machines runs, they do not care about expressiveness of the variable names again, and camel case versus snake case or tabs versus spaces arguments, as long as the syntax is valid. Business people or our clients, right, which was a common answer, they do not care about the big O notation and polymorphism as long as instructions that you wrote do get the job done within required constraints. Actually, what was really pleasant, the most common answer I saw in chat, you write code for other programmers to read, understand, and modify. You write code for future version of yourselves to read, understand, and modify. The designs of the software system range from quite simple to extraordinarily complex. The more complex the designs, the greater the cognitive load placed on the programmers. And this cognitive load is called the design weight. The greater the weight of this design, the more time and effort is required for programmers to understand and manipulate the system. So this quote, usually attributed to Albert Einstein, it's often used as an appeal to make a subject as easy as possible to understand, though not, of course, so easy that it becomes meaningless. It's an important part because when we are talking about simple design, we are not talking about absence of design either. Applications that hooked with a single 15,000 lines long file of code that intersects between each other is not simple by any means. It has no design instead of having simple, and places a big cognitive load to the reader. And by the reader, we mean programmer. That the programmer that has to modify its behavior, and in order to modify it, it has to understand it. Applications that has so many layers of components that it's hard to comprehend, and therefore change is not simple either. So let's look at several ways to make our designs simple to understand and, most importantly, simple to change. We will start with a middle layer of code. We'll be talking about classes and what methods should and should not belong to the classes. There are two ways to address the middle layer: the S.O.L.I.D principles and design patterns, and both do complement each other. The S.O.L.I.D principles tell us how to arrange our functions and data structures into classes, and how those classes should be interconnected. But the word that I use, class, doesn't imply that these principles are applicable only to object-oriented software. The class is simply a coupled grouping of functions in data. Every software system has such groupings, whether they are called classes or not. The S.O.L.I.D principles do apply to those groupings. The goal of these principles is the creation of mid-level software structures that tolerate change, are easy to understand, and are the basis of components that can be used in many software systems. The first lateral letter in S.O.L.I.D stands for single responsibility principle. It's an active outcome of the Conway's law. The best structure for the software system is heavily influenced by the social structure of the organization that uses it, so that each software model has one and only one reason to change. Of all of the S.O.L.I.D principles, the single responsibility principle might be the least well understood. It's likely because it has particularly inappropriate name. It is so easy for programmers to hear the name and then assume that it means that every module should do one thing. Make no mistake. There is principle like that. It's a good and important one. A function should do one and only one thing. We use this principle when we are refactoring large functions into smaller ones. We use it at the lowest levels, but it's not one of the S.O.L.I.D principles, and it's not single responsibility principle. Historically, the single responsibility principle has been described in this way. A module should have one and only one reason to change. Software systems are changed to satisfy users and stakeholders. Those users and stakeholders, or in a more general words, actors, are the reason to change. In that and they are the reasons principle is talking about. Perhaps the best way to understand it is by looking at symptoms of violating it. Look at this example. This class violates single responsibility principle because those three methods are responsible for three very different actors. The calculate pay method is specified by the accounting department, which responds to the chief financial officer. Reporting hours method specified and used by the human resources department, which is under chief operational officer. And the safe method is specified by the database administrators who reports to chief technical officer. By putting the source code of three methods into a single employee class, the developers have coupled each of those actors into each other. This coupling can cause the actions of the chief financial officer's team to affect something that COO team depends on. For example, suppose that the calculate pay function and report hours function share common algorithm for calculating non-overtime hours. Suppose also that the developers who are careful not to duplicate code, because, don't repeat yourself stuff, they put algorithm into some sort of algorithm for calculation into a separate single function. Let's call it regular hours. Now suppose that the chief financial officer's team decides that when non-overtime hours are calculated needs to be tweaked. In contrast, the COO team in HR department does not want this particular tweak because they use non-overtime hours for a different purpose. You see the problem here? The change was requested by one of the stakeholders and it affected the output of another who would not know about this update. Multiple months and wrongly calculated salaries can pass before inconsistent overtime calculations will be detected by someone, and it potentially affected hundreds of people. Now imagine that two different stakeholders require changes simultaneously and they are conflicting. So two different engineers in two different teams, they do this change. So at the very least, you end up in a merge situation. There are many ways and solutions to this problem. Each moves the functions into different classes. Perhaps the most obvious ways to solve the problem is to separate the data from functions. The three classes share access to employee data, which is a simple data structure with no methods. Each class holds only the source code necessary for its particular function. The three classes are not allowed to know about each other, thus any accidental duplication and merges are avoided. Now, in order to work with a single class instead of three, which is inconvenient, you can use the facade pattern. The employee facade contains very little code, just responsible for instantiating and delegating to the classes with the functions. There are more than one way to achieve this, as I told already, but the principle is same. Scoping the functionality related to the same actor or actor together. Single responsibility principle is about functions and classes, but it reappears in a different format to more levels. At the level of components, it becomes a common closure principle. At the architectural level, it becomes access of change, responsible for creation of architectural boundaries. On the other hand, if you put in what you put in a single module or component or a microservice instead of a single class, and how you arrange related functionality of multiple services and classes and components and modules. Okay, open-close principle. The gist is that a software system to be easy to change. They must be designed to allow the behavior of those systems to be changed by adding new code, rather than changing existing one. In other words, the behavior of the software artifact ought to be extendable without having to modify that artifact. This, of course, is the most fundamental reason that we study software architecture in the first place. Most students do recognize this principle as one that guides them to design classes and modules, but the principle takes on even greater significance when we consider the level of architectural components. Imagine for a moment that we have systems that displays financial summary on a web page, right? The data on the page is scrollable, therefore it can feed some enormous amount of data, and the negative numbers are rendered in red. Now imagine that the stakeholders ask the same information to be turned into a report printed out on a printer. It's black and white printer, so report should be properly paginated, and we cannot allow to have red symbols there. So negative numbers are in parentheses, and we should have proper footers and headers and column labels. Clearly, some new code must be written, but how much old code will we have to change? Well, the good and simple system design would reduce the amount of change code to barest minimum, ideally zero. How do you ask? By properly separating things that change into for different reasons. Remember the S.O.L.I.D single responsibility principle we just talked about, and then organizing the dependencies between those things properly. The dependency inversion principle we will talk about shortly. The essential insight here is that generating the report involves two separate responsibilities: the calculation of the reported data and the presentation of this data on web or printed friendly form or whatever. Let's look at the diagram. Having made this separation, we need to organize the source code dependencies to ensure that changes to one of those responsibilities do not cause changes in the other. Also, the new organization should ensure that the behavior can be extended without undue modification. We accomplish this by partitioning the processes into classes and separating those classes into components. If component A should be protected from changes in component B, then B should depend on component A. We want to protect the controller from changes in presenters. if we want to protect presenters from changes in views, if we want to protect interactor from changes in, well, everything. The interactor is in the position that best conforms to open-close principle. Changes to the database or controller on presenters or views will have no impact on this interactor. Yeah. If you know the Gang of 4 design patterns, you can recognize the version of the MVC pattern here. Here, the interactor would be called a model. The open-close principle is one that's driving forces behind the architecture of systems. The goal is to make system easy to extend without incurring a high impact of change. And this goal is accomplished by partitioning the system into components and arranging the components into dependency hierarchy that protects higher level components from changes to lower level components. Let's move on to Liskov substitution. In short, this principle says that to build software system from interchangeable parts, those parts must adhere to a contract that allows these parts to be substituted one for another. The original definition is very mathematical and makes hard to understand by majority of readers, me including. So here we can see the human readable and more concise one. This design, you can see on the slide, conforms to the Liskov substitution because the behavior of the billing application does not depend in any way on which of the two subtypes it uses. Both of the subtypes are substitutable for the license. However, the canonical example of violation of Liskov substitution principle is the famed square rectangle problem. In this example, square is not a proper subtype of a rectangle because the height and width of the rectangle are independently mutable. In contrast, the height and width of the square must change together. Yes, I understand the calculation of area and so on, they have the same, but interface is different. Since the user believes it is communicating with a rectangle, it could easily get confused. The only way to defend against this kind of LSP violation is to add mechanism to the user, such as like if of statement or case statement that detects whether a rectangle is actually a square. The interfaces can be of many forms. We might have a Java-style interface implemented by several classes, or we might have Ruby classes that share the same method signatures, or we might have a set of microservices that all responds to the same REST API. So this principle forces us to build our hierarchy of entities based not on the entity type, but on its interfaces. A simple violation of substitutability can cause a system design or architecture to be polluted with a significant amount of unnecessary extra mechanism to detect what kind of entity I'm talking to. So it's turn for interface segregation. This principle advises software designers to avoid depending on things they don't use. The interface segregation principle derives its name from this very diagram that you can see right now. So let's assume that each of the user classes here, user 1, 2, and 3, uses only one of the methods from ops class, op 1, 2, and 3 correspondingly. Now imagine that ops is a class written in a language like Java or C#. Clearly, in that case, the source code of the user 1 will depend on functions op2 and op3, even though it doesn't call them. This dependence means that a change to the source code of op2 in ops class will force user one to be recompiled and redeployed, even though nothing it cares about has actually changed. The problem can be resolved by segregating operations into interfaces. But the more grounded and less academical example, however, can be JavaScript module exports of utilities. Here we can see the difference in the same code, but written in different versions of the Firebase SDK. In the old one, you import the whole Firebase app. More so, there are a few modular imports like Aus and Firestore, and they have side effects because they are adding functionality to the Firebase object. So the order of imports is important here. Because if you try to import Firebase Aus first, it will not compile. On the right is an example of usage of version 9 of the Firebase SDK. We import from app and the Firestore packages only the functions that we really need at the moment. During this build process, unused content from the packages is stripped away via a process called tree shaking, and this approach allows the Firebase team to reduce the bundle size to up to 80% and have less interconnected dependencies. If you take a step back and look at the root motivations of the interface segregation, you can see a deeper concern lurking here. In general, it is harmful to depend on modules that contain more than you need. You will find that it's a recurring issue soon enough. Consider, for example, an architect working on a system. He wants to include a certain framework into a system. Now suppose that authors of this framework have bound it to a particular database. Or what is more commonly some big heavy ORM. So system depends on the database or ORM indirectly. Now suppose this database contains features that framework does not use, and therefore system does not care about. It's a problem also of full stack frameworks that give you everything out of the box regardless if you need it or not, like Symfony and Doctrine, or Ruby on Rails and Active Record, or Laravel and Eloquent, or Spring and Hibernate. You got the point, right? So the lesson here is that depending on something that carries baggage that you don't need can cause you troubles that you don't expect. The code that implements high-level policies should not depend on the code that implements lower-level details. Rather than details should depend on policies. This is what dependency inversion is about. Clearly, treating this idea as a rule is unrealistic, because software systems must depend on many concrete facilities. For example, string class in Java. It's a very concrete class, and it would be unrealistic to try to force it to be abstract. The source code dependency on this concrete Java length string cannot and should not be avoided. Same goes for window local storage in a browser JavaScript API. It is very concrete. You wouldn't expect to have some sort of interface there, right? However, we tolerate those concrete dependencies because we know we can rely on them not to change. It is the volatile, concrete elements of our systems that we want to avoid depending on. Those are the modules that we're actively developing and that are undergoing frequent change. Every change to an abstract interface corresponds to a change to its implementations. Conversely, changes to concrete implementations do not always or even usually require changes to the interfaces that they implement. Therefore, interfaces are less volatile than implementations. Once again, it's not about or only about the classes and modules. It can be interfaces between groups of microservices or third-party integrations with public APIs. You may need to fetch data from external API and implement the fetching directly in the place that requires it, or wrap it in some sort of abstraction with a stable interface. Then, if the third-party API is changed or needs swapping for another one, you change implementation or create new implementation without updating an interface, as nothing depends on the implementation details. Another example is unit testing. You mock the dependencies for the tests with your stuff. Just keep your interface and you're good to go and achieve this 100% coverage. So you may already notice the design patterns work to basically implement the S.O.L.I.D principles. They're common solutions to common problems. And we are talking about the simple code. It doesn't mean that implementation has to be flat. We already saw during the examples in a previous section that we often were adding more classes and interfaces into the design. Same with patterns. They often require some very specific structures with a hierarchy and so on. But they do reduce the cognitive design weight. How do you ask? Well, for starters, they are familiar solutions to the common problems. When someone explains to me how he made a system and mentions that it is built with MVC pattern, I do not need to think twice about how code is structured. I know how it is structured for a fact, regardless of the technology framework or language. But also they do allow the S.O.L.I.D principles. They do follow the S.O.L.I.D principles in implementation. You can challenge me on this in the comments. Don't worry, I'm not going to go through each of the gang of 4 design patterns here. Otherwise, we run out of time and you run out of meeting. Instead, let's move on to simple components. So let's zoom out a bit. If the S.O.L.I.D principles tell us how to arrange the bricks into the walls and rooms, then the component principles, they tell us how to arrange rooms into buildings. When I'm talking about components, depending on the context, it may mean a jar file or DLL, or what you put in a separate module in NPM or Composer or Gem or whatever. It can also be a microservice. When we operate with a small enough microservices and not distributed monoliths, the unary element of a deployment, that's what is a component. What happens when we are trying to apply the same approaches to components? Well, we will have a slightly different set of principles to reach the same design. So reuse release equivalence principle. Imagine that every one of you use this one, so maybe not with like not knowing it. When I began my software engineer career in 2013, it was totally okay to share code via classes on code sharing websites. Not like Stack Overflow or GitHub, but rather Code Canyon and the free HTML alternatives. To an extent that during some interview, I was asked how to access AWS S3 bucket with PHP. And well, I've told the name of the class I found online for this very purpose, instead of using the official SDK. Just to find out that the company actually uses the same class, probably from the same website. Maybe another one, because it was common for the same class to be distributed on multiple websites. Nowadays, however, we have all sorts of package managers. New languages that are released like Dart, Go, and Rust, they're shipped with the package managers. Like NPM took over the world, and it's hard to imagine Java project without Maven or Cradle. It's also common to create private repositories for the project in-house dependencies and the same package management systems that we use for the third parties, like NuGets, yeah, private NuGet repositories or whatever. But what stays the same is versioning. Yes, I found the very same class I'm talking about, the S3. The reuse release equivalence principle is a principle that seems obvious, at least in hindsight. People who want to reuse software, components, they cannot and will not do so unless those components are tracked through the release process and are given release numbers. This is not simply because without release numbers there would be no way to ensure that all the reused components are compatible with each other. Rather, it also reflects the fact that software developers need to know when the releases are coming and which changes those releases will bring. So we invented systems to mark releases like Samware and so on. This also means that the classes and modules that are formed into a component must belong to a cohesive group. However, there is another way to look at this issue that it perhaps not quite so obvious. Classes and modules that are grouped together into a component should be releasable together. The fact that they share the same version number and the same release tracking should make sense for both, author and the users. Prefer to have smaller libraries and modules which belong to a cohesive group of functionality and are changed for the same reason. We will discuss this part shortly, actually. You will find that some are being modified quite often and some are effectively stale. And they do not require any change or re-release, almost never. So with a big library or somehow irrelevant functionality like common utilities module, you release it as often as the most frequent part of that needed a change. But let's move to the next principle, common closure one. This might be obvious on the first glance, and it is easy to make analogy with solid principles here. It's basically a single responsibility principle restated for components, just as a single responsibility principle says that class should not contain multiple reasons to change. So the common closure principle says that component should not have multiple reasons to change. And by reasons to change, you remember, we mean actors who require those changes, stakeholders. If the code in the application must change, you would prefer that all of the changes occur in one component rather than many components. If a change are confined in a single component, then we need to redeploy only the one change component. Other components that don't depend on the changed one, they don't need to be revalidated and redeployed. So according to this one, prefer to have bigger and fatter components that can contain all of your changes in one go. Next one is common reuse. It states that classes and modules that tend to be reused together belong to the same component. Classes are rarely reused in isolation. More typically, reusable classes collaborate with other classes that are part of the reusable abstraction. This principle states that these classes belong together in the same component. In such a component, we would expect to see classes that have lots of dependencies on each other. The simple example might be a container class and its iterators. Those classes are used together because they are tightly coupled to each other, though they are to be in the same component. But common reuse principle tells us more than just which classes to put together into component. It also tells us which classes not to put together in a component. When one component uses another as a dependency, dependency is created between the components. You know, when we have like two components and one relate to each other. Because of this dependency, every time the used component is changed, the using component will likely to be changed as well. So the common reuse principle is a generic version of interface segregation that we just talked several minutes ago. The interface segregation principle advises us not to depend on classes that have methods we don't use. The common reuse principle advises us not to depend on components that have classes we do not use. So in simple words, do not depend on things you don't need. Remember the frameworks and RAM example? It's still a thing here. Though it was not, I wasn't completely honest. Those ORMs are usually separate components from the frameworks. Often you can drop them from installation. Rarely, however, you can replace them as a separate entity. But it's not part of the core framework, at least in those examples. And it's really, usually it's hard to use them away from the frameworks as well. So the component principles I've just described, you could notice they do fight each other. Like some of them do tell us to have a smaller components, and some they tell us that have bigger and fatter components. It's better and have less changes during the release, right? So you can see this tension between the principles on the diagram. The edges of the diagram describe the cost of abandoning one principle to the opposite vertex. Trick is to find balance that fits your current needs. But be aware that those needs and concerns will change over time. For example, early in development of the project, the common closure principle is much more important than the release equivalence, because developability and having less components that have to be changed during the deployment, it's more important than reuse. Generally, projects tend to start on the right side of this triangle, where the only sacrifice is reuse. As the project matures and then projects begin to draw from it, the other ones, then projects tend to slide, to the left part. This means that component structure of a project can vary from time and maturity, and it has more to do with the way that project is developed and used, not with what project actually does. The big part of the software development also is not only making the changes, but also delivering those changes to the users. So it has to be built in a way where release is boring and routine as possible. So yeah, how to achieve this? Let's look at a few examples again. Here, the simplicity aspect states that any change you have to do has to be as small as possibly it can be. So for every large change you want to decompose it for small incremental steps, and that are much more manageable. You want to make sure that each one of those steps maintains the backward and forward compatibility of data and interfaces, because while making those changes, you do not want to break the interface to anyone who's relying on your services and interfaces. So your intra-team communications are simple to manage, or simpler at least. And also keep in mind that on any large-scale system, it is normal situation where multiple versions of the same service commonly coexist in production. Every release effectively is a rolling release. Your Kubernetes or Elastic Container Service or whatever you use, they do not replace service instances immediately, but like one by one. Your front end is not propagated through CDNs worldwide in an instant. It takes time. More so, your single page apps are not refreshing the page of the user as it does not turn off the browser window for weeks in a row. And I'm one of those users. Your mobile app is not updated in all of the users' phones immediately. So transitional states are a norm and not an exception. Feature flags is a powerful tool for you to control what features users will get to use. It also enables you to have better control over the development and delivery process. By decoupling the code delivery from feature delivery, you make your deployments and changes simpler and safer. It doesn't matter that only backend is deployed and DB is not seeded just yet or not yet have migrations if this code is not executed. It allows you to rapidly turn features on and off, like without 30 to 60 minutes of redeployment. It also allows you to verify the feature in production before enabling it to the whole user base. Or even what we did when I worked in CRG. We made a system where new features were toggled not only per customer, and I'm talking about B2B business. So some customers were getting new features quicker or vice versa. Some were able to prepare their end for the new features, but also some percentage of the users. So let's say we would release a new feature that becomes a major part of the booking creation process. And we were enabling it for like 3% of the users. If there were no crashes, notifications in the monitoring system, etc., we would enable it for 10% of the users, then 50, and so on. It also allowed us to calculate the cloud resources better in the system that is under high load category, but any standard, as we could see the real gradual resource demand. And as we allowed more users to land on this new microservice or whatever. On the other hand, if something goes wrong, we were able to quickly disable the feature until the next release, and only a small fraction of users were affected. But also it allows us to verify the business metrics and compare the results. What was the KPI of the old versus new way in the same day, or so it kind of combined our feature flags and canary deployments style of delivery system, while all of the code was shipped into all of the instances. According to the research that Microsoft did several years ago, the developers do spend about 75% of time on reading an existing code while working on the systems. The 20% of time modifying the existing code and only about 5% of time on writing completely new code. Tests do allow you to make your changes simpler and work faster, as you can fail fast and see the problems as soon as they appear. They also help you to understand the code base better because test becomes documentation and code usage examples at the same time. Also, according to Michael Feathers, author of the Working Efficiency with Legacy Code, there is a deep synergy between testability and a good design. All of the pain that we feel writing unit tests points to underlying design problems. And it's totally true. Uh, by the way, this book is about legacy system. It's actually about unit testing. So do test-driven development to make your life and system simpler. And you're free to ask questions. I know it's been a lot of content and you're tired and so on, but yeah, you're free to raise your hands and ask questions. Anatoly.
Yep.
Yes.
Hi there. Nice presentation. I think I pretty well know the source it's taken from. My question
I
is
stated at the beginning the source. Yeah.
Yep. So how do S.O.L.I.D principles apply to functional components, specifically to React? How can we apply those? Apparently, it's pretty much simple for the single responsibility principle, but how about the others? For example, list of substitution. Thank you.
Well, the thing is that, as I told, I was most of the time talking about classes, but as I stated at the beginning, any logical groupings would fit in here. You replace word class with a word component, and it still kind of works. Yes, and you pointed it right. Some are easier than others, but when we're talking about list code substitution, uh, you may not have inheritance in the sense of the OOP, but you have components that may share, in your case, a same interface. Or if you resort to this, they may share the props class that has, the same props class if you're using the TypeScript. Or if you're not using TypeScript, of course, just they have, same signature, right? If you're in the situation where you have to, juggle them for to have different displays of same data, that's pretty much it. I remember about on the previous project here in ELEKS, one of the features I built, the search functionality for the system. So it was a big system. It searched through different entities. So designers wrote some sort of mock-up for the design. Everything is fine, and then I'm implementing it, and we do realize that different entities. We had entities like a transaction and an invoice and a user. So the information was similar on those rows. And when designer makes it, it looks awesome because they make exactly the data that fits all the columns and so on. But in the real world, suddenly data from transaction and invoices, well, some of it made no sense. So simple, by using this list code substitution principle, by having a different components for rendering a single row and different type of components based on what kind of entity is there, I would, render them in a different way. The line of data that would come from the search, it had a same pattern. And the component knew how to use the low-level data correctly. But how, in OOP, I would have inheritance into a number of classes with the same interface. Here, they all had a same method signature, but I could replace them and swap them to show the specific, the specific type of data. That's a very direct example of what you just asked.
Okay. Okay. Just one more comment. Like would like to see far more live JavaScript examples in such a presentation, because yeah, it's kind of, at least for me, it's kind of difficult to abstract away from the diagrams to the code and back to the code and following the quick speech.
I understand. Thank you for the feedback.
Probably give us some code examples and a few, 15 to 20 seconds to pause and to think about what's going on and how we can improve on that. Otherwise, great presentation. Thanks.
Thank you for the feedback. I was actually purposely trying not to bind the content to the specific language or technology. The whole SADO is invited to this talk with the different languages and backgrounds. So I will consider your feedback and implement it for the next tech talk. Thank you. Is there anyone else?
Thank you. You have possibility to ask questions now, so we are waiting.
Okay, you know how to find me. My contact data is here on the screen, and yeah, you can ask questions in comments as well. Thank you for your time, and thank you for joining, guys. And see you on the next one.
Thank you, Iurii, for your time and your experience sharing with us. And guys, I ask you to please fill our feedback form. It's very important for us. So, and it will be good for us and Iurii to read your good feedbacks. We hope it will be good.
Or bad feedbacks. Like I also want to improve my presentation skills. Yeah. Great.
Just feel free to share with us your opinion and have a good end of the day. Bye, everyone.
Cheers.
Bye.
Thank you.
Thanks.
Thank you. Bye.
Thanks.
Bye.